Hello and welcome to the Engineering Career Coach Podcast. In this episode, I have the pleasure of talking to Jeff Doolittle, a software architect and transformational leader with more than 20 years of experience designing and architecting software systems. We'll be talking about the importance of complexity in engineering and how engineers and engineering leaders can contain complexity in their organizations. I'm your host, Jeff Perry, founder of More Than Engineering. I help engineers and technical professionals create careers and lives that they love. And this is the Engineering Career Coach Podcast. This is the first podcast dedicated to helping engineers and tech professionals with both their personal and professional development. Before we get started, I just want to mention that this is a free show and our sponsors help us to keep it free. So I would now like to recognize our sponsor for this episode, Washington State University.
Washington State University's global campus offers a high-value online educational experience in engineering and technology management. The ETM program offers a master's degree and graduate certificates in specialty areas like industrial leadership and supply chain management. Courses provide technical professionals with the knowledge, tools, and skills to manage projects, operations, organizations, and people. The program is tailored for professionals who want to advance their careers while still working full-time. ETM faculty and staff are accessible and personable from first contact through graduation. The program is well recognized and provides courses taught by faculty with industry experience. Live interactive learning provides industry-relevant content, giving students immediately applicable skills. Engineering and technology management, an advanced degree for an advanced workforce. Accelerate your career and reach out today.
Now it's time to jump right into our main segment of the episode. Today I'm so happy to be here with Jeff Doolittle. Jeff and I have known each other for a little while. Jeff, it's so great to be with you today. Thanks for coming on the show.
Hey, Jeff. Really excited to be here. Thanks for having me.
Yeah, and you've got a great name, I just got to say.
I agree.
Yeah. So Jeff, welcome. And in your own words, help us get to know you. Tell our listeners who you are, a little bit about your career journey up to this point.
Sure. I started on software and computers by breaking my dad's computer back in the 80s and started building websites in the 90s when I was in college. In fact, the first job I had was building a website for a company, and they paid me with a Dell desktop computer, Macromedia Dreamweaver, Adobe Illustrator, and Photoshop.
Nice.
And they decided to hire me on as a software engineer. And after a few years, I actually became the CTO of that consultancy. And ag tech kind of adopted us in food processing because of the region we were in. And so we ended up having that be sort of the primary industries that we targeted, and learned a lot about those verticals and those industries in those years. Later on in the late 2000s, I became the CTO of a SaaS startup, also in ag tech, and had a few different products that we launched along the way, some spectacular failures, or what I like to call learning experiences,
Sure.
And then some moderate successes as well. And after just being burnt out on consultancy, which, the feast or famine syndrome, and SaaS company, which is the constant just flood of things to do, and the terror of trying to raise venture capital, these kinds of things, finally decided to take a little bit of a break and go back to being an employee. So I started at Trimble Viewpoint as a software architect in late 2019. And that's where I've been throughout the pandemic. And I also completed a Master of Arts in Transformational Leadership in 2010. So that's kind of my convergence of leadership thinking, business leadership, software leadership, and that kind of coming together for me in the sense of championing quality and customer value, basically focusing on certain values like repeatability, reversibility, automation, trust, clarity, and empowerment. Those are kind of my summary of the things I'm after.
Very cool. And we were just talking before we started how where you're at now, Trimble Viewpoint has a lot of ties into other engineering industries. Can you tell us a little bit more about that as far as the software solutions and how that connects to other industries?
Yeah, Trimble started about 43 years ago, and it was primarily in the hardware space. And so they may not be the most well-known household name, but for people in engineering or IoT, wasn't called that then, but what we now call IoT, Trimble was a known company for quite a long time. They shifted more to a software acquisition company for the second 20 years of their existence. And so that's where this transition kind of began. And those software companies were mostly left to operate independently within the broader holding company, if you will. Now the strategy has shifted towards creating shared functionality and shared capabilities across, well, first off, within different verticals like construction, transportation, logistics, natural resources, and ag, and then also even across the entire company as well. So there's lots of fun challenges and opportunities with taking an organization that was literally built to be siloed and then transitioning to being a company that is breaking apart those silos and finding ways to collaborate across the organization.
Wow, very cool. So could be some fun things as we talk about some of the principles around how do we deal with some of these big problems on the larger scale and bring people together.
Yeah, for sure.
Now, Jeff, you also are one of the hosts of Software Engineering Radio. It's a podcast. Can you tell us more about the show and how this has benefited your engineering career, like being a part of that?
So much of what we do, whether it's software engineering, civil engineering, structural engineering, mechanical, a lot of it comes down to communication. Mm-hmm. And one of the greatest things about having a podcast is it really highlights the ways that you're not good at communicating, or at least where there's chinks in your armor that you can sort of shore up. So it can be little things. For example, stopping to think about filler words instead of constantly having to say something. Just pause for a second, and it actually comes off in a way that doesn't really off-put people. Clarity of ideas, economy of words, things of this nature have been really helpful. I think one of the big aspects for me as well has been learning to be receiver focused instead of sender focused.
Okay, what would you say that means? Help us understand that.
So sometimes when we communicate, we're trying to make sure that what we think is being understood and putting it out in a way that we would understand, I think is part of the issue. That's sort of the first impulse often. But instead, shifting that impulse and saying, how can I present this in a way that is receivable by that person and understandable by them, even if it's presented in a package that maybe wouldn't be the way that I would receive it.
Okay, interesting. I like that. That's good. Okay. And anything else that's been helpful as you've been a part of this?
Sure. Access to industry leaders has been another big one. Okay. The ability to contact certain individuals that you used to consider superheroes in your industry, and suddenly they respond. That's pretty amazing and humbling opportunity to have. And that ability just sort of, I don't know how quite to sum it up. It's amazing. It's humbling, but it also, after a while, sort of feels normal. Mm-hmm. And so that's kind of a neat place to be. And then having that access and exposing people to those good ideas, especially for individuals who maybe aren't as well known as they used to be or probably still should be, has been a really amazing opportunity.
Okay, very cool. So I want to get into some different topics here. And one of the things I think we're going to talk about a lot today is this idea of complexity and how complexity in engineering organizations can create some challenges in their systems and other things. So can you talk to me and kind of set the stage for some of the challenges of complexity in engineering and technical organizations?
Sure. And I'll say that from my perspective, just playing my cards a little bit, my sense is what we call software engineering would definitely benefit from more emphasis on the second word.
Okay.
Oftentimes the focus is on the software side of things, the technologies or the tools, sometimes the practices or methodologies that come with the software industry as it currently exists. And often that engineering side of things is not always emphasized and often not even taught. There's many schools that have computer science programs, but they don't have corresponding software engineering programs, which is interesting because you don't want a biologist to be your doctor. You have a doctor to do that. You don't have a chemist to be your chemical engineer. You have an engineer for that. So in a similar way, there's a gap in the software industry that many besides myself have recognized. And so I'd start there. And I mentioned that to say, my sense is that engineers often have a better grasp on the concepts of complexity than maybe most others do because they've been exposed to mathematics. They've been exposed to limits, constraints in the real world, things that have to be taken into account. Engineers ask a different question than most people. A lot of creative people who like to put things together ask the question, how do I make this work? Engineers ask a very different question. What is going to go wrong? How can I break it?
Or how might other people break it if I don't do this right?
How's it going to break?
Yeah.
Exactly. And so that kind of leads into complexity, which is there's various, when you think about ordered systems and as they move to maybe a state of chaos or a state of disorder, there's a spectrum there. Some things we have a sense of control over, and sometimes we all know what to do. Other times, maybe there's different ways of approaching it, but they're all somewhat equally valid. And then you get to a point where we're going, we really don't know what we're doing. This is beyond human capacity to comprehend. And you think about large numbers, for example. So here's a concept I would say is an engineering concept, but oftentimes doesn't always apply in the way I see people building software systems. So here's the example. Imagine you have 7 components in a system. Okay. And they're similar, say they're similar in size or scope, or just, 7, which is good for the human brain because 7 is about all we can hold in our heads at a given time.
Okay. Maybe you, that seems low.
Well, 4 to 7 is what the psychologists and the cognitive scientists tell us from what I've read. So let's say 7. So if you design a system that has 7 elements in it, now let's imagine that there's no constraints on how those 7 elements can interact with one another. Mm-hmm. If you have a system like that, there's 5,040 possible combinations and permutations of those 7 components in different configurations. Now, since we can only hold 4 to 7 things in our head at a time, 5,040 is a pretty large number. Now, here's where it gets scary. Let's do a simple thing and just double that. And this is where complexity bites us, because we don't inherently understand things like the law of large numbers, the exponential or geometrical nature of certain real world phenomena. Humans cannot comprehend it. We can sort of ponder it and think about it with abstractions, but we can't really ponder it. So now take that simple 7 and double it to 14. There's over 87 billion possible combinations of those 14 components. Mm-hmm. Now, here's the question. How many software systems out there have what are called microservices and have way more than 14 and have no restrictions on the interactions between those components? Wow, okay. I would say most. Mm-hmm. And so there's kind of the fundamental thing that often bites software systems. This can also bite organizations as well. There's something in the software industry called Conway's Law, which states basically the idea is software organizations will build systems that reflect their own communication structures. Mm-hmm. And this can apply to any organization as well. So the challenge of complexity isn't just a software problem. It's a human challenge. But I think it affects the software industry in some specifically troubling ways that could be beneficial if there was more thinking about complexity and engineering discipline applied to it.
Yeah. I'm just thinking, as you apply this to humans and the people in those organizations, you talk about those 7 or 14 components in a system, but what about those 7 or 14 people in a team or in a division or an organization? And then how much bigger that is when we're talking about dozens or hundreds or thousands or tens of thousands of people in an organization, just how complex moving all those parts and how those different permutations, how those people can or won't interact.
Absolutely.
And the processes around that to do that well is amazingly complex. So let's look at this then and start breaking down what complexity looks like. So you and I talked about and looked at you would describe this as 5 different sources of complexity. So we want to break these down a little bit. The first one being technological complexity. So can you walk us through what technological complexity is? Let's start there, and the impact that it has on technical and engineering leaders and teams.
Sure. Real quick, before I dive into technological complexity specifically, I'll say what the goal is. And again, this is something engineers often get implicitly or inherently because of their training. The goal is to contain complexity. There's something called the law of the conservation of complexity. You never actually get rid of it. All you can actually do is shift it around. And the irony is that when something is too simple, I remember Einstein said things should be as simple as possible and no simpler. I believe it was Einstein. So the irony is when we make things too simple, all we're doing is shifting the complexity to somebody else. So think about this example, and this will kind of lead us right into technological complexity. Imagine a car that was designed by very lazy manufacturers, we'll say, and they want the user to have to stitch things together in order to make the automobile run, because they don't feel like actually creating simple interfaces for their end user. So now, and this is a bit absurd, but imagine that you actually have to control the timing belt. You have to control the fuel injection. You have to control the rate of the carburetor. You have to, all of these things, the timing of the spark plugs. That would be a almost impossible car to drive if anybody could. You'd have to have expert knowledge. Maybe you're the only person who knows how to do it in your organization. These kinds of problems. Mm-hmm. And unfortunately, that's often how software is designed and developed. And if those principles are applied in an engineering context, people die or things break and it costs a lot of money. And in that case, people's lives now have suffering involved, which can also lead to death. In software, we often don't see those directly. They still happen. They're just less obvious that the consequences are happening. And so what often happens is, to reduce that complexity, you hire what's called a front end team. And now inside the dashboard of your car, literally right there, you plug everything together right in the dashboard. So instead of just being gauges and dials telling you the state of the system, they're literally putting together the parts in the state of the system in order to provide you with this ability to drive. That's the state of most software now, is you have these various elements that are stitched together in a front-end application, and that's delivered and said, woohoo, we delivered something to our customer, and yet it's brittle, it's fragile, it's nearly impossible to maintain, and it gets worse with time the more people mess with it.
Okay.
So that's where we get into technological complexity. I describe that by saying it's the excessive reliance on technologies and tools, especially new shiny ones. Neil Ford is a guy in the software industry, and he's quoted as saying, software engineers are like moths to a flame, often with the same result as it relates to complex. I didn't say it right. Software developers are to complexity like moth to a flame, often with the same result. There we go. Okay. I botched it, but you get the idea. And so sometimes if we're obsessed with our tools or our technologies or a pattern or a framework or something we've seen before that worked here and it must work here now, then what you're going to get is a system that has a lot of technological complexity. Maybe there's a high burden of understanding some part of this system, or maybe there's an integration of parts that's unclear. My uncle, before he passed away, years ago, he worked for Sandia National Laboratories, and he also worked for Livermore Labs. And at one point, he worked for a medical device company. And he was an engineer, one of the smartest people I've ever known. He was literally a rocket scientist, right? Yeah, people say, it doesn't take a rocket scientist. Like, well, my Uncle Jerry here, he is a rocket scientist. So we had wonderful conversations. And for a while, he worked for a medical device company. And they would ship these medical devices, I don't remember exactly what they did, all over the country. And it was funny because every single one, well, in a sense, it wasn't funny. Every single one of them was a one-off. So what would happen is when somebody would call and say there's something wrong, they couldn't say, pull out the manual, here's the diagnostics, go to this part of this machine, push this button, change this wire, whatever. They had to send out a diagnostician to every single site to inspect what it was, look at how it was integrated and implemented in that site, and then guess, hope, with enough intelligence, seeing enough things, they could often fix it. Sometimes they couldn't. So I say this to say that is, again, a lot of software projects. Yeah. But it isn't just software. This was a company that had engineers in it. Now, by the way, my uncle was not responsible for designing this thing. He was brought in to try to help fix the problem. But I remember him saying to my father-in-law at one point, he said, we don't know what we're building. Right. And that's how technological complexity can really start to bite you. Even in the real world software is the real world, but even with physical items as well.
Yeah. And so, I mean, we're still talking about technology in different contexts, right? So then we have the technological complexity, a lot of things that we love the bright, shiny tools and different things we think are going to solve all of our problems. But then as you're talking about that analogy of the vehicle and bringing things to the front end and a dashboard and software or vehicles or whatever, we have to bring these different pieces together, and you talked about stitched together. So it's integration. So let's move to this next one, integration complexity. What, as we bring different pieces together, how does that bring more complexity into the system?
Yeah, I started kind of going there a little bit with the previous analogy. The sense there with technological complexity was somebody picks some special component that they like and they plug it in, and it's different than what somebody else did. That's where the technological this is new shiny. Let's use this now instead of that. Mm-hmm. The integration complexity comes in back to that analogy of the 7 items, or the 7 components, the 14 components, where if you have this overabundance of components that are connected together with a lack of consistency, that's a problem. Mm-hmm. Or there's no cohesion, meaning the sense of this is what this thing does. And there's a simple interface to, say, a fuel pump, right? Well, what happens? Well, fuel goes in and fuel goes out. Okay. And back to the question most people would ask, how do we make it work? And engineers say, no, what about corrosion? What about flow rates? What about back pressure? What about right throttling? What about all these things that we would ask about a fuel pump? And so a lack of cohesion, what does this thing do? And does it encapsulate that thing that it does well in a way that's easy to integrate with? And then also a lack of constraints, like I mentioned before, things like flow rates or corrosion or things of this nature. And so again, these are engineering concepts that often engineers fundamentally grasp. Good engineers, understand, and they apply these all the time. And in software, when people don't do this, you get to a dark and depressing place I call microservice mayhem, where now you just have all these random parts that are just kind of thrown together, and you get a Rube Goldberg machine. And again, unmaintainable. Nobody understands how it's integrated. They don't understand how to fix it. And it's a heavy burden to try to maintain if you can maintain it at all without making it worse.
Wow. So that sounds fun. And then we add on this next layer of the people.
If you're sadistic, maybe. Yeah,
yeah, right. And hopefully I'm not really. Maybe just a little bit. But then we add in the next layer, and it's the organization. It's the people. Yeah. And you mentioned Conway's Law earlier, of like, in particular, software systems reflect the communication structures of the organization. So we bring in a software that only mimics like how we're already operating, rather than considering how should we actually do this well. And that's just one way that we bring in more complexity. So talk about how the people and the organizational structure adds another layer of complexity, and what that looks like.
Absolutely. And on top of what you just said, there's also this issue of alignment and reality versus correspondence. Okay. Very often a company has a stated organizational structure.
Yep.
But if you want to know what their actual organizational structure is, look at the systems they produce.
Yeah.
Mm-hmm. Honestly, that's the telling reality. If you look at the systems, you'll know what the real communication structures are. I don't care what management hierarchies there are. I don't care who reports to who. So here's an example of organizational complexity. We create these teams and we say they're going to be working on their own thing, and they're going to communicate with very simple communication protocols between them, right? This is kind of the Amazon thing, right? What does Jeff Bezos call it? The two pizza team. But then all those engineers are talking directly to each other all the time. All of the managers are not filtering information. They're having customer feedback go straight to the software engineers or the software developers. And so now you may have these stated organizational structures, but the real organizational structures are back to that kind of rat's nest. It's funny because it mimics that integration complexity again, right?
Yeah.
So now there's integration everywhere. This is a house where all the cables are running through the house, the power cables, the Cat5, the plumbing. And, sometimes that's cool in a coffee house when that's up above you, maybe certain kinds of plumbing, not all of it, but some, right?
Yeah.
But in a home, that's not really what you want. And so that's where organizational complexity can kind of bite you, is if you don't have some sense of maybe control is not the best word, but some influence and some ability to guide and watch and adjust as you go, then you're just going to sort of let the natural whatever happens. And that's going to result in a system that's not going to be, consistent, cohesive, and properly constrained, like I mentioned before.
Okay. So people and how they work and the systems that surround that are going to be amazingly complex, and not actually spending their time on things that are worthwhile and getting the right things done.
Not if you don't help them organize in a way that contains the complexity,
sure.
Right?
Yeah.
And really that's the heart of what a lot of the software industry has tried to do with things like self-organizing teams. Mm-hmm. But often those self-organizing teams are not provided with what I call liberating constraints. So, maybe for the story before, the kids who were put in a playground and the fences were taken down because the theory was kids will feel more free if the fences are taken down. And all the kids huddled in the middle of the park. When they put the fences back up, the kids spread around and they used the entire playground. So what does this tell us? It tells us that their feeling of safety was important for them to feel free.
Yeah.
Now, you can go too far with that. Okay, I'm not making a political statement here, but I'm saying there is a sense that for you to feel free, say in your family, a relationship with a spouse or a significant other, if there's not some sense of safety, then there's a lack of freedom. So in a similar way, if we don't have some constraints, and they need to be checked because they could be the wrong ones, but at least you need to have them and be reevaluated from time to time. But if you don't have them, you're just sort of saying, well, we're going to get what we get.
Yeah. Constraints, another word I'd use, personally and in teams, is boundaries. It can help us feel appropriately safe in different situations, build some psychological safety in teams and other things. So that's great.
Yeah, that's a form of a constraint. And then, like I said, those communication patterns, what flows in, what flows out, what stays inside. There's so much more power when you put things behind an your car is easy to drive because all that complexity has been handled inside the engine and inside the interconnection of all the parts for you. And when that is not working, that's called a quality problem.
Mm-hmm. Yeah.
So in the same way with software, if something's not working because the user doesn't know how to drive a car by manually putting everything together themselves, or the dashboard is failing to stitch these things all up together, right? Well, it's actually a quality problem. And if the engine itself has these problems, it's the same thing.
Okay. So far we've gone through 3 of the 5: technological, integration, organizational. Next one, want to kind of get into, can you lead us through talking about operational complexity, what this means and what that looks like?
Yeah. In fact, quality is a perfect segue to that. So a lot of software projects experience maintenance burdens that get more difficult and more costly with time. And again, this would be true in a physical system as well. A poorly designed system that was not designed with quality in mind is going to suffer from operational complexity. So operational complexity would be this: we're going to build a car manufacturing company and we're going to buy a bunch of equipment and a bunch of tooling, and we're going to throw a bunch of people in a factory, big warehouse, and say, build us a car. And self-organize and go for it. We're not going to constrain the organization or the integration or the technology. We're just going to say, go. Great, outcomes car. So right, it's an opaque box. We don't have an outcomes car. We say, cool, now let's send that to our quality assurance department, which is in software, they call it that, but it's actually the wrong name for it. What it really is your quality control department, which is a very important thing because the people who get to crash the cars are very smart people and they have a lot of fun. But I'm going to tell you right now, as smart and as wonderful as they are not smart enough to solve a quality problem that late in the process. This is called operational complexity. A lot of software teams as well are not responsible to maintain the software that they ship. This naturally leads to operational complexity. When the person who builds the system is responsible to operate the system, this has a natural reducing effect on operational complexity. So the ancient Babylonians were really smart about this. If you built a bridge, your family had to live under that bridge for a year.
Wow.
Again, so what you do is you align the incentives, you have skin in the game, and you're going to make sure that the operational complexity of that bridge is greatly reduced, because if it collapses on you, you're going to pay the price. So that's how operational complexity comes about and again, the analogy of the car company was a bit absurd, but I'm not kidding you. A lot of software projects are done exactly that way.
Yeah.
And so now what happens is, well, how do we reduce our cloud costs? And how do we simplify our operational deployments? And how do we? Mm-hmm. But hold on. And those aren't bad things to do. But the cost of doing those things is orders of magnitude greater than catching a problem in the design before you even build anything. And by the way, that's quality assurance. It's design integrity from the beginning. And then it's empowering everyone in the organization to be able to say there's a quality problem and be rewarded for it when they do so.
So this whole idea of like the design team's going to focus on design, then they throw it over the wall to the maintenance team, whatever you want to call it, and they're on to the next, and the design team's on to the next project. My hands are, I'm washing my hands of this, no more. That is one way that we can create more operational complexity.
Yeah, and then it's feedback loops as well.
They don't always consider how they build it with an eye for maintainability and quality and things there, because they won't have to own it once they get it off their hands. Is that right?
Yeah, and that's why car companies test quality at every step of the process. They test the individual components. They test multiple components put together in different configurations. One of my mentors uses the analogy of an airplane. If they built you an airplane and they just tested the whole plane, would you get on that plane? That's all they tested was the whole plane. The answer is, of course, no. If they built you a plane and they tested every individual component, but that's all they tested, would you get on that plane? No.
Yeah.
Okay, they build the plane, they test a few integrations, they tested it. No, they test everything. Now, I will grant, not every software system is necessarily going to require that level of discipline. However, software systems that we deploy oftentimes grow beyond the wildest dreams of the people that created them.
Yeah.
And just a little bit of design can help save you a lot of pain later. The cheapest defect or the cheapest time to discover a defect is in the design phase and the requirements phase before you build anything.
Yeah. I remember a few years ago when I was in software, a peer of mine, and we were talking about like, we don't need to worry about that. No one's ever going to use it that way. And my peer said, he's like, don't underestimate the ingenuity of complete idiots. Like, you just never know how people are going to use, because it's not going to be, in many cases, it's not going to be in any way that you would think people are going to use your systems. And we're talking about software, we can talk about any other product or system or piece of infrastructure that engineers might build. You just never know what might come your way, and need to design with some of those things in mind as much as humanly possible. So very good.
Well, and real quick on that, remember that you're also the idiot.
Yeah, exactly.
So Richard Feynman has a great quote that I love, and I probably say it too often, but he says, the first thing is not to be fooled, and you are the easiest person to fool. It's a good reminder.
Yeah, great point. So number 5 in these sources of complexity is the market. Like, hey, what are we experiencing external to us? What's the market telling us? So talk to us about that a little bit, and then we certainly want to get into how do we create these constraints and containers on complexity a little bit. But let's talk about it first.
Sure. Before we dive into that real quick, just a bit of a side note. There is a difference between incidental complexity that sort of we add to a system. And all 4 of those prior sources of complexity can be subject to a general idea of accidental or incidental complexity, meaning the system may just be complicated. It may not be complex, but we made it complex because of our technological choices, or the way we decomposed our components and then integrated them, or the way we organize our organization, or the fact we waited until the end to try to deal with things at the operational level. So in that sense, it's possible that in those previous areas that you could be more of a complicated domain. Yeah. As soon as you throw in the market, you're in a complex domain. Markets fail, nations fall, despite what people think. No empire in history has survived forever, and they never will. So things are complex in the market. So we take these software systems that we build, and then we put them out there in the world where there's natural disasters, where consumer preferences can change, where stock markets can crash, where new forms of currency, or is it a currency? There's a whole debate there. Right. All of this complexity. And so when we put our systems out there into those environments, this just adds a whole nother magnitude of complexity. And I mention it here because my sense is that it's very helpful when people building software and building systems generally as well, cars, back to that as well. It's helpful when they understand the nature of the people that they're serving. Yeah. And it's helpful when they understand the nature of the complexities that will affect those people as individuals and also as groups. Automobiles, it's not just you and your car, it's you and all the other cars on the road. And it's the complexity of what can affect your safety and your comfort and your drivability and all of these things along the way. So that's a similar concept with market complexity.
Yeah. Okay. Very good. So let's look at the others. The other side of this. We've talked about how challenging complexity is and these different forces and factors that come into this. So how do engineers actually move through this and contain and put these appropriate constraints to manage the complexity in their organizations? What are some of the ways they can do this?
Well, I'll say I am first going to mention that those 5 may not be every source. Sure. They're the 5 that I've come up with. And in the same fashion, these 4 are 4 that I've thought of, but this is an invitation to a conversation. Once again, a good engineering discipline is to seek invalidation rather than validation. Yeah. And so for your designs, by the way, that's a great way to improve quality. Yeah. Get more eyes on it, get more criticism of it. Iron Man this thing, make it stronger. So in a similar fashion, we're just
the idiots who have this idea for right now, and we need some help to shore it up.
Yes. Assume you're wrong. The idea is to be less wrong, right? Yeah. So what are some ways to contain complexity? So first, I'd start with this. And again, this is something I think engineers do implicitly. They may not call it this, but this is something software desperately needs is to identify capabilities. Software architects have been talking about this for a while, and it's a little tricky because it's hard to really nail down what is a capability. A lot of words are just bandied about, and there's not necessarily a shared understanding of them. The risk is we say the same words, so therefore we think we mean the same thing and we move on. Right. Yeah. By the way, that's a bug in the requirements when that happens, and that gets into your design, and then that ends up in operational complexity down the road. But I digress. So what are capabilities? I'll say this. first, you need to know generally, what are you trying to build? What's its purpose? What's its goal? And what you want to do is recognize what nature does when it makes decisions. Nature tends to seek the fewest number of possible components or capabilities in order to solve a problem. Not always, but generally speaking, that's the trend that we see over millions of years. So in a similar fashion, when we're designing systems, we should be thinking about what are the minimum number of capabilities that can be integrated together in order to solve the main problem I'm trying to solve. And the beauty of when you do this as well is now you can start to look at similar cases that maybe have some variance to them and say, could I solve this same, or could I solve this other problem using a different configuration of, or some extension of these existing capabilities? And then you keep doing that. And this is back to that idea of invalidating your model. So you don't assume you got it right the first time. In an interesting way, back to the automobile analogy, there's a lot of capabilities in automobiles now that were sort of implicit previously. We didn't have a fuel injector system, but fuel still got into the engine. So it was less controlled, but the same concept was there. We didn't have a starter with a key, but you had to get on the front and you had to crank the, right? Crank the crank.
Yeah.
So the idea here is to say, let's identify those capabilities and let's discover the minimum possible number. And then finally, one of the great things about this for both a software or a physical system is sometimes you identify a possible way to have fewer capabilities to solve a problem. You can now use that as an evaluation and an analysis tool to look at what you have and the ways it doesn't align with that and start strategizing. How could we start moving in that direction over time with either our new design for automobile or with our upcoming changes to our software system? So you can incrementally move towards this. This isn't just a way to design new systems. It's an evaluation tool to help you improve existing systems as well.
Okay, interesting. Okay, so we've identified the minimum number of capabilities we need, and then what? How do we move through with some more containers and constraints here?
Yeah, so it actually is to enforce constraints, and first you have to define those constraints. This again is where in the physical world of engineering, constraints are going to naturally be right up front. There's going to be budgets. There's going to be time frames. There's going to be actual land or material or equipment or individuals that are involved. There's going to be quality metrics. There's going to be just general. Some buildings don't need to stand up in a 9 Richter scale earthquake, and some do. So there's those things as well. Like, okay, what are the right constraints for this project? I'm just building a shed in my backyard. I don't need to use I-beams. I don't need to drop pylons down, 30 meters into the ground. Okay, right. So it's defining the right constraints, and then it's enforcing those constraints. And so very often in an attempt to just build some software and get something shipped, and by the way, there's a place for this. I'll say, if you're just exploring an idea, that's great. Go for it. Go build some proof of concept, and that's fine. The risk comes is no engineer in the world takes this model that they built of the bridge that they're going to build and then says, ship it.
Right.
Because you can't. Unfortunately, in software, you can. The question is back to, it's like Jurassic Park, right? You never stop to ask whether you should.
Yeah.
And so there need to be some constraint. And that's one of them that I would say is another important constraint for software is we will not ship this. We refuse to ship this. What we will do with this exploration, this proof of concept, what we will do is we will learn, and it will refine our understanding of the capabilities that we need to deliver. So it goes back to the capabilities. Maybe there's a way to reduce the number of capabilities or enhance one of them a bit. And there's that beautiful dance now between, do we have the right constraints? Well, let's go back to our capabilities. How does that fit? Okay, let's tweak these. Let's change these. How does that work? And now you're actually exploring those capabilities with some actual putting together of technologies and systems to try it out and invalidate it again.
Okay, very good. And what about the people here? The people need to work together. How do we make sure that they're on the operational and the organizational level, in particular, if we're going back to the layers of complexity? How do we bring them together and put those right constraints there?
One of the fundamental principles in the universe that we see over and over again is something that's called encapsulation. And an example is a cell in your body. That's a complex piece of machinery. Okay, well, maybe it's not a machine, but it's a complex piece of, right?
Biology, we might just say.
Sure. There, thank you. It's not hardware. It's soft. It's not software either. It's wetware.
Yeah.
So it's a complex piece, but then, what does that do? Well, it has certain ways of communicating within itself, and it has certain ways of communicating between itself and other cells, or even different kinds of cells. Now, imagine if you don't clarify communication between your cells and the other cells in your body, or you don't differentiate the types of cells within your body, or the cell is emanating all this information about what's happening with your mitochondria and your endoplasmic reticula, and it's like, it's a mess. It's just, you're not going to live first. You're not going to get life emerging from that. There has to be some sense there of doing that. So ironically, when encapsulation was first proposed over 40 years ago by a gentleman named David Parnas, it was actually seen as not the way people do things in the software industry, but it's how the world works. But it doesn't matter. That's not how we do things in the software industry. It took a while. People came around, and now people talk about encapsulation, but it's back to, are we really saying the same thing when we say that word? Mm-hmm. And so true encapsulation is where you've encapsulated this capability, right? Or the set of capabilities, and you've constrained them appropriately, and you've clarified what stays inside the boundary and what exits the boundary. And one of the most important, and this applies to human teams as well. Mm-hmm. One of the most important ways, or one of the most valuable ways to extract the most from a team and to allow it to be the most effective, is to define and clarify what communication stays inside the cell and what communication goes outside and comes back in from the outside. Mm-hmm. That right there, just as a fundamental way of thinking about teams, is critical. And so anything you can do to say, define that contract, right, or the connecting point between teams, mm-hmm. and then define what stays inside and what goes out. And now you get Conway's law on your side. Now your services will reflect, your systems will reflect that communication structure. And now you're going to naturally be encapsulating things that you should be encapsulating.
Okay, very good. So I think you said there are 4. We've talked about identifying those capabilities, enforcing the constraints, encapsulation or clarifying that communication. And what's the 4th one here to help us contain complexity?
Yeah, the 4th one is to commit to vigilance. And part of that for me is an empowerment step or an empowerment philosophy. I mentioned before the need for quality to be something that everyone in the organization is empowered to care about and also to take action for. Toyota back in the 1950s, there was a gentleman from the United States named Edward Deming. He's the father of quality assurance, total quality management. And in the United States, they didn't think they needed his ideas. Well, right. Little did they know, eventually they would adopt them. So he went to Japan, and a lot of our listeners probably know the rest of the story. He literally transformed the Japanese automobile industry. What's funny is Ford and GM, I believe, went to visit, and they actually let them come. And they saw scrums and stand-ups and Kanban boards and these things, and they brought them back. And how did they do throughout the 50s and 60s relative to Toyota? Toyota continued to thrive, and they did not. They went back again, and they noticed something they missed the first time. It's something called the andon cord. It was a red cord that was along the entire factory line, and every single person was empowered to pull it if they noticed a quality problem. And even if there was no quality problem, the employee was rewarded. So commit to vigilance, first off, is not something that you say is your job individually as, say, a software architect or an engineer, although it's partly your job, but it's everyone's job. All the stakeholders need to be guided, empowered, equipped, trained to identify complexity and to understand ways that they can help elevate it when they see it, or try to solve for it by containing it. Again, you can't get rid of it, but like moving it to a place that's appropriate. And when you do that, then it's very important that you reward effective complexity containment strategies. We don't need swoop-ins. We don't need heroics. We don't need some magical individual that knows how to do this. We need individuals that are empowered to think this way about how to contain complexity.
Yeah, I love that. Okay, we talked about a lot of different stuff. So we end off kind of this main segment of the episode. Any other final advice that you would give to engineers and engineering leaders who are trying to manage complexity well?
I think first off, finding books on systems thinking generally, and I can give you some links later to some that I have found helpful. But just that idea of systems thinking, and then learning to think that way as almost a game that you play just during the day. I mean, I gave you a few analogies, and I can't stop thinking about systems now that I've sort of got the bug. Mm-hmm. And it sort of becomes this gamified way of sort of thinking about what's the system of that guitar behind me? What's the system of these instruments together? What's the system of this house that contains those things? And what complexities are contained, and what complexities sometimes crop up? And I say, maybe I should deal with that, right? Mm-hmm. And so I think thinking about and reading about systems thinking generally, also because getting a common language around that is really helpful as well. When you're learning similar concepts to your colleagues and you're able to actually look at the systems that you're designing and building and have a similar frame of reference. I think the other one is not blindly adopting processes or practices or ceremonies that maybe worked for someone else or worked somewhere else. Akin to what the auto manufacturers from the US did when they visited, Japan back in the 50s. Look at how it's actually going to help you and find ways to measure that, find ways to qualitatively and quantitatively determine, is this working for us or not? And if it's not working for you, have the boldness and the honesty to say, this isn't working. How can we do better?
Right. Yeah. Okay. I like that. Well, this has been a fun conversation. At this point, we're going to transition into this Take Action Today segment of the show, where we'll get one final piece of advice and something you can take away from our conversation today. We'll be right back. Now it's time for our Take Action Today segment of the show. Jeff, we've had a fun discussion, but what would you suggest for people who are just starting out here to take action to really start managing complexity and getting into systems thinking? What would you suggest they do and take action on to get going on this?
I think one of the best things you can do first is to find someone to go on the journey with you. It's just sort of like, I'm glad you're with me, Sam, from Lord of the Rings. Frodo's not going it alone. It can feel lonely sometimes, especially in the software world. I imagine aspects and elements of the engineering world might not have the same kinds of problems, but I've seen them. They are there. So find someone else who's interested in complexity and interested in learning about it and interested in invalidating their own assumptions with you, and vice versa. And now you build this beautiful relationship where you're almost sparring together about your ideas. And it's not about us together pushing on our creative ideas and our creative thinking to improve it and to make it better. And in that context, get training on systems design, get training on systems thinking, read the things that you can read on these things, and start bringing those things together with this other individual, and then find the next one and the next two and kind of go from there.
Yeah, perfect. Thanks so much, Jeff. This has been a fabulous and fun discussion. I've learned a lot, like I do almost every time we get to talk.
Oh, thanks.
Except for that one time.
Yeah, you didn't learn anything that time.
Yeah, but such a fun discussion, and hope people take something out of it. If people want to connect with you or learn more about what you do and other areas, where would you point them to?
The simplest place is my website. It's my name, jeffdoolittle.com. Jeff Doolittle with 2 O's, not like the infamous veterinarian. Yeah, and that's about it.
Okay.
Find me there.
Thanks so much, and take care. Wishing nothing but the best as you keep moving forward. Thanks so much.
Thanks, Jeff. Appreciate it.
I really hope you enjoyed the episode today. We would love to hear your feedback, comments, and questions. You can go to www.engineeringmanagementinstitute.org, where you'll find a summary of the key points discussed in the episode, as well as links to any of the resources, websites, or books that we mentioned. And don't forget to check out any upcoming live webinars, also at engineeringmanagementinstitute.org. Additionally, for any engineers who are struggling and need help taking the next career step, I've created some free training resources with an opportunity to join a more intensive program called the Engineering Career Accelerator. You can find more information at engineeringcareeraccelerator.com. Until next time, I wish you the best in all of your engineering endeavors.